Hello. I'm going to talk to you about dark photons in a Higgs-Stueckelberg model for dark matter. The question is, what is the true nature of dark matter? In particle physics, the idea is that the concept of a weakly interactive massive particle called the WIMP could be the candidate of dark matter. A recent result coming from the xenon collaboration has stirred the field of dark matter, particle dark matter, with the observation of an electronic recoil that could be interpreted as a measurement of a dark matter particle. They actually observed an excess in the KeV region, which they interpreted as possibly a solar axion, or maybe a large neutrino magnetic moment. Of course, if everything went wrong and it was a false result, they're still looking for the possibility of a contamination from tritium atoms. Anyway, these are the possible scenarios that could lead to the detection of a dark matter particle. In this seminar, I will try to argue that this axis could be attributed to a fermionic WIMP in the so-called Higgs-Stueckelberg model that we studied some time ago. Particle dark matter detection is a tricky thing. If you try to detect it directly, you can imagine that our galaxy is surrounded by this dark matter halo, and as the sun and the solar system move through the halo, they feel a kind of WIMP wind, and this WIMP wind can be detected in local detectors. So this is basically the idea of what is called direct detection. So the aim of particle physics is in a certain sense to define a microscopic model that can explain the astrophysical observations. In particular, our model, we were studying what is called the beyond standard model, where we take the standard model and we introduce new U1 vector bosons, which generically are called dark photons. Our model extends the known gauge groups of the standard model, which you have the SU3 color part, the SU2 weak sector, and the U1 electromagnetic. And these three gauge groups are enlarged to include two new gauge groups of vector particles. This is what we call the Higgs-Stueckelberg model. And of course, this model has its name because of the way the particles get their mass. So if I can make a small picture of the particles involved in this model, we have these the standard model represented by the quarks and the leptons and the gauge forces. In our model, we have these extra particles. There's this singlet fermion and two vector bosons, the Z prime and the gamma prime. The Z prime is a massive vector particle, and the gamma prime is a photon-like massless particle. So now we'll briefly review the idea of the Stueckelberg mechanism. So consider, for example, this Lagrangian. This Lagrangian could represent a vector particle, for example, the photon, but it has a mass term, so the mass term enters with the gauge field with the mass squared. Of course, under local gauge transformation, one transforms the gauge field by the standard transformation, which leaves the first term of the Lagrangian invariant. It's an easy exercise to check, but it's obvious by inspection that the massive term is not invariant. So the mass term breaks the gauge invariance. So in principle, you have to figure out a way, an alternative way of introducing mass to vector particles. So let's consider the previous Lagrangian, but with the modification. In the place of the mass term, I have this lambda term, which is contracted over the mu index. But now the lambda term is actually the replacement of the mass times the gauge field. And it has this extra term, which is the so-called Stueckelberg field. Of course, there's in the modified Lagrangian the free part of the Stueckelberg field, which is a scalar field. And the thing is that under gauge transformation of the usual gauge transformation of the gauge field, supplied with the following transformation for the sigma field, this Lagrangian, even though it has mass, it is invariant under this transformation. So this is a mechanism that allows you to have a vector particle, a massive vector particle with a mass introduced in the Lagrangian, and still you guarantee the gauge invariance. Of course, this is more tricky if you have non-abelian fields. So in principle, you have to, for non-abelian fields, you have to have the Higgs mechanism. So this is why the model that I'm going to describe to you next is a mixture, a hybrid of Stueckelberg and Higgs mechanisms. So the basic idea of the model that we studied is that you have the standard model particles and you have this dark matter sector. In the dark matter sector, you have this chi fermion, which is a singlet. We consider that the chi fermion has a small electric charge and also carries the dark charge, which allows it to interact with the dark photon in the dark sector. But in this intersection, you have Z prime that actually lives in both worlds, in the standard model and in the dark sector. This is a brief overview of the Lagrangian. The Lagrangian of our Higgs-Stueckelberg model is written by three terms. There's the standard model modified term, the Stueckelberg term, and the chi Lagrangian for the fermion field. Here in below, you can see the actual Lagrangian for the modified standard model sector. It is the usual standard model Lagrangian, but with these blue fields, these blue quantities that are the modified terms. I mean, we have the usual SU2 bosons, the vector boson, and now there's this new C boson, which appears here, and we modify the covariant derivative. Of course, the phi that appears here is the usual Higgs mechanism, usual Higgs field, I'm sorry. And, and in the derivative, you have the field with a GC coupling. The Stueckelberg term is similar to the one that I showed you before, but now we have this vector part of this X field, which is a massive term, but now the massive term has the original Stueckelberg field and the C boson and the X boson. So the C boson before the breaking of spontaneous breaking of symmetry is in both sectors. It appears in the Stueckelberg Lagrangian, and it appears in the extended standard model too. And here is the chiral, the chi fermion, which will be our WIMP. It has the usual fermionic Lagrangian within interaction with the current interaction, and GX is the the coupling constant. There are two gauge fixing terms that are included in the Lagrangian. Okay, now imagine that spontaneous symmetry has been broken. You can gather all the vector terms into the Lagrangian and form this mass Lagrangian where the, the four vector fields are present. X and C are the new dark particles, the new vector bosons that are included. B and W3 mu are the usual standard model part. The matrix of the mass squared is given by this term, where there is a parameterization on this phi angle. So now, imagine that I take the GC equal to 0. This means that the dark sector will decouple from the standard model, and this can be seen in the mass matrix where it's block diagonal. You can see the upper block is represented by the dark sector. The lower block is the usual standard model sector. And if you calculate the eigenvalues, the mass eigenvalues, you will find 4 values. In the dark sector, you have two bosons, one which is massless, the other one which we will call the Z prime. And in the standard model sector, the usual 0 mass photon, which is the standard model photon, and the Z boson also appears. Now consider that the GC isn't 0, but it's small. So the mass matrix can be diagonalized and expanded as a power of GC. And you find these two contributions to the Z prime mass and to the Z mass. So you have this arbitrary quantity that is the correction to the Z mass, but the Z mass is something that's very well known. So this means that this contribution that comes from the dark sector must fall into the uncertainty of the Z mass. You can see that in this F function that appears here in the Z mass, there is the mixing angle that I showed you before, and there's this epsilon quantity, which is the ratio between the Z mass and the Z prime mass. So in principle, if we want to have a parameterization of the Z prime mass and have an estimate of its value, we must know how much, how is the variation of this F function. So the experimental value, as I said, the Z boson is very well known. We can extract it from particle data group, and it has this value. And the correction to the Z mass is this small value in GeV. So this means that this is the value that will fix this term that corrects the Z mass from our model. You can look at the very simple case. Consider that phi is 0. So and set F to 1. To lie in the error corridor, one should have that the MC that appears right here, proportional to the GC coupling, should have the value of 618 MeV. So we see that having this fitted, one has that the F function should be bounded below and -1 and +1. So this is the restriction that will determine the epsilon. This epsilon is actually, remember, the ratio of the Z mass to the Z prime mass. And we can make a graph just to see it as a function of the epsilon. And observe that the F as a function of the epsilon always has this lower bound that is -1. So we can estimate the minimum value of the z prime mass by setting the f function given by this relation to -1. So that expression can be calculated for the minimum value of z prime as a function of the z and as a function of the mixing parameter. So for example, if I choose that phi is equal to 0, this will give me that the minimum value that the z prime mass can have is actually the z. So it means that the masses are degenerated. Now, if we consider the maximum value that phi can have, that is pi over 2, the z prime, the minimum value for inspection of the z prime has an interesting value that it's very close to the Higgs boson mass. It's 128 GeV approximately. And remember that the Higgs mass is 125 GeV. So now let's come to an application. We have studied this model in an astrophysical scenario, and this scenario was related to white dwarf cooling. You see, white dwarf cooling can be studied by a field called asteroseismology, which is the study of the oscillation in stars. Different oscillation modes are sensitive to different parts of the star, and they give us information about the internal structure of the star by the observation of small variations in the star's brightness. So if an astronomer is observing the star, he looks at the radiation that the star emits, that basically are photons, and these small variations in brightness of the luminosity can give you information about the interior of the star. So in principle, the star, if it's a white dwarf, it's cooling and emitting radiation that the astronomer is seeing. But it could happen that if the star has dark matter or some other content for its composition, which is not ordinary matter, it could be emitting radiation that is invisible to the astronomer. So this could mean that there's a part of the radiation that is invisible and could give origin to an extra cooling mechanism. Recently, Corsico and collaborators used the state-of-art model of asteroseismology to study cooling rate of an anomalous pulsating white dwarf star, which is given by the G117b15a. And they considered that this invisible radiation is actually emission of axions. Axion is a particle which has a long story in particle physics, and is one of the candidates being searched as dark matter particles. So in principle, their study was to consider that this anomalous cooling is responsible for the emission of axions. This can be calculated in a simple manner by this energy loss formula, where here you have rho, that is the density of the star. There's this convolution of the boson part and of the photons with electron part. You see, in the process considered for stellar cooling of the white dwarf, it's an axion-Compton process where the electrons in the white dwarf interact with the photon being converted into this A particle, which is the axion. The axion actually enters via cross-section in this formula. So this is a way of calculating the energy loss. And by doing this calculation, you can infer, as Corsico and collaborators did, a mass for the axion. And they obtained 17.4 milli electron volts, approximately 20. This is a very good estimate, the, uh, considering that this is actually a measurement, but it's an excellent estimate compared with many models that consider that the axion actually has a mass approximately in the range of milli electron volts. In our calculation, we did something similar. We considered that the white dwarf was filled with a part of this chi matter, these dark fermions that were inside the star with the ordinary matter. And considering that the chi particle carries both electric charge, a small electric charge, and the dark charge, in principle, a Compton-like process is possible, where the photon can be absorbed by the chi fermion and transformed into a dark photon, which is the invisible radiation. So the formula is very similar. The difference is in the cross section that we must calculate this process, and this was done. And the interesting result is that looking at this graph, we have this, the black line is the axion emission, and these colored lines, red, green, blue, and black, and dark blue, are actually the different contributions that can come from the dark photon as a function of the mass of the chi. And these curves, to be at the same order of the axion, must have a mass of the order of keV, kilo electron volts, ranging from 1 to 10 kilo electron volts. And this C that appears here is just the ratio of the dark charge to the electric charge. And this is a free parameter of the model, as the mass is too. Now, independent from what we've done, Ruffini and collaborators have studied the dark matter content distribution in the core and the halo of galaxies. And they considered in their model that the dark matter is composed of basically fermions. And to match the observed results, they inferred which would be the mass of the fermion to match the observations. And they arrived at, surprisingly, the same order of that we have, about 10 kilo electron volts, which would be the upper curve, but still in this range of keV. So we have, from two independent sources, two independent models, trying to fit the astronomical data. We have the idea that there is a light fermion content that could be inside anomalous cooling of anomalous white dwarfs, and could also be the dark matter observed in galaxies. Now, coming to our conclusions, and this is where I shall speculate a little bit about the Zenon result. We have shown that it is possible to consider that the emission of invisible radiation from white dwarfs could be from axions or from dark photons. But to have a dark photon, you must have a fermion, a dark fermion, a WIMP sort of particle, with a mass in the range of 1 keV to 10 keV, which is consistent with data from galaxies. So we argue that the recoil energy of keV measured by Zenon could be possibly understood in our model as an interaction of the chi particle with electrons by an exchange of a photon, uh, uh, and producing a recoil. So this could be studied by this process. So the next step to check this is to run a Monte Carlo where we will actually calculate this explicit diagram inside our model and check it running the background to see if the excess coming from this process is consistent with what Zeno has observed. Thank you.